All right, we're going to parameterize a curve with respect to its arc length, starting at a certain point. Actually, what we are doing is reparametrizing, because when we are writing a curve with respect to t, as t the independent variable, then that is already parametrized. So what we really want to do is rewrite this formula, whatever it is, so that the independent variable is the arc length. So think of this as the arc length. And this, think of it as time, perhaps. Yeah. And so we want to have an accurate equation, equality between those two, where the input, sometimes you want to know where the point will be after certain length on the curve versus where the point will be on the curve after so much time. So that is the difference. Um, the difference is that here the input is the length from a certain point, while here the input is the time from a certain point where the time is 0. So let's get started. I'm gonna start with example 2. Example 1 was the one in the previous video, 5072. That was example. That's where we had example 1, and now we are on example 2. We want to reparametrize, reparametrize um, r of t, which will be cosine t, sine t, and t over 2 pi with respect to WRT will be a shorthand way of writing with respect to S, the arc length, starting at 0, 0. Oops, sorry. It doesn't start there. It starts at 1, 0, 0. As t increases. So the picture we have, we're a little familiar with this, is like this. So this goes around. If we project those points down to the floor, we're going to end up with a circle of radius 1, center at the origin. But instead, we have this helix going up, moving up. So by the time we get here, we would have circle around 1 revolution. That will happen when t is 2 pi. And when t is 2 pi, the height, this is the z value, will be 2 pi divided by 2 pi, which is going to be 1. So the starting point is 1, 0, 0. And the ending point after 1 revolution, of course, this continues to more revolutions as t increases. But after the first revolution, the ending point will be same x and y coordinates, 1, 0, 1, 0, and then 1 unit up here. Yep. All right, it does help to compare this graph or this function with the projection of this on the floor. So I'm going to call a new function. So let's compare to p of t, which is going to be equal to cosine of t, sine of t, and 0. That is a projection of this helix on the floor. So there you go. We start in the same spot, 1, 0, 0. But as t runs around, well, as t increases, we run around, and we end up in the same spot after 2 pi. When t is equal to 2 pi, we come back to the same spot. Here, when t is equal to 2 pi, we climb up And we don't end up with the same spot. We end up with something that is lined up with the beginning, but 1 unit above. So let's find S of t first. Let's find a relationship between S and t. So S of t is, we're going to use the formula from the previous videos, the last 2 videos. We're going to go from 0 to t. And let's go back to the function. We have cosine. We cannot use t anymore for the integration because t is a limit, so we have to change the variable. It is a little bit of a technicality that we may not use the same variable of integration as part of the variables on the upper or lower limit. We have to have a different variable. So let's use u instead. So pretend you have r of u equals cosine of u, sine of u, and u over 2 pi. And remember how we find the arc length. Take the derivative. So we have negative sine of u. We're going to have a square root here. Parenthesis, negative sine of u squared plus, and then derivative of sine will be cosine u squared, excuse me, plus, I'm going to continue down here. I'm running out of space. So the root, this is the line of the root, continues. And then we have u over 2 pi. The derivative of that is 1 over 2 pi, and we're going to square that. So plus 1 over 2 pi, and we're going to square that. That's the end of the root, and then that is with respect to u. That's kind of a little weird. Let me rewrite it down here. The reason why this looks really weird is because the root got broken up into 2 parts. So it's really, again, square root of negative sine u squared plus quantity cosine u squared plus quantity 1 over 2 pi squared du rather. Because the variable, the upper limit contains t. We may not have t. We have to use a different variable. Okay, now we need to simplify this. This is really sine squared because the negative vanishes after we square. So this is sine squared of u, cosine squared of u. So those are going to be 1. So we have this, the integral from 0 to t of the square root of 1 plus 1 over 4 pi squared when we distribute the square du. That is a constant. All of this is a constant, 1 and the pi and the 4. All of those numbers are constant, so we can factor them out. So that is the square root. As I factor this out, let me split up the 1 as, or rewrite the 1 as 4 pi squared over 4 pi squared. So we can add those fractions together. So I'm just rewriting the 1 down here. And I'm exiting this out of the root. So we have just du from 0 to t. And we're just integrating 1. Integrating 1 just gives us t, u rather, and then we're going to plug in t. I don't want to dwell too much on that. But let's continue here. 4 pi squared plus 1 over 4 pi squared. And again, this is 1. The antiderivative of 1 with respect to u is u. We're going to plug in t. And then we're going to plug in 0 and subtract those 2. So we end up with the square root of 4 pi squared plus 1 over 2 pi, because here we're going to be taking the square root of the numerator, the square root of the denominator. The denominator does simplify, the numerator does not simplify, and we multiply by t. So we end up with S being equal this constant, square root of 4 pi squared plus 1 over 2 pi times t. So we have a strong relationship between S and t. Yeah. We can rewrite this equation in terms of S. So let's put it here. And this means that t is equal to 2 pi divided by the square root 4 pi squared plus 1 s. We can multiply by the reciprocal, so we can solve this equation for t. All right. And the reason why we want to do that is because we want to reparametrize, we want to rewrite the curve, not in terms of t, but in terms of s. See, back here at the beginning, we said we want to rewrite r, not in terms of t, but in terms of s. We don't want to have t in the picture. We want to have s in the picture. Just like here, we don't have s in the picture. Now we want s in the picture. And this is the way to achieve it. First, we find a relationship between t and s, and then we replace t. So r of t will be, as we know, cosine of t, sine t, and then t over 2 pi, this vector. All right, but we're going to replace t with this. So it's going to get a little, not very pretty. It's going to be the cosine of t, which is 2 pi over 4 pi squared plus 1 square root s, comma, sine 2 pi over square root 4 pi squared plus 1 s, comma, and then t is this guy. And then when we divide by 2 pi, the 2 pi will vanish. So we end up with s over square root 4 pi squared plus 1. Whoa, I barely had room to write that on one line. Okay, so that is now a function of s. Notice that here only s shows up, s, s, s. There's no t, at least not explicit t. There's a hidden t because after all, this is t, this is t, and here it's not so clear what t is because we already simplified 2 pi. So this is, so we can finally, so the parametrization, yeah, the reparametrization of r with respect to s is, and then we can rewrite it, r of s is equal to, man, I have to write a little smaller, cosine of 2 pi over square root of 4 pi squared plus 1 s, comma, sine 2 pi over square root 4 pi squared plus 1 s. Man, I did not have enough room to put my third coordinate, so I'm going to continue underneath, s over square root of 4 pi squared plus 1, and then close the parenthesis of the vector. So we have first coordinate, this is the x coordinate, y coordinate, z coordinate. It just didn't fit in one line very well. But that is the parametrization of the curve r with respect to s. Okay, let me go back to the projection. Remember the projection we wrote down on the first page of this video? Here we have the projection on the floor. We're calling that p of t, which has cosine of t, sine of t, and 0. Let me write this down here. So p of t equals cosine t, sine t, 0, and that is just a circle on the floor. As t increases, we draw the circle And it just keeps going around and around as t keeps increasing. So we get a full revolution when t equals to 2 pi. So here's 0. When t is equal to 0, we get 1, 0, 0. And then we go around. And when we come back to 2 pi, we come back to the same point when t equals 2 pi. It turns out that if you go 1 unit, if t is equal to 1 unit, if t is equal to 1, then we will end up with a point maybe somewhere around here. So this is going to be r of 1. And this is really the unit circle. If you look from the top, this is a unit circle. And so the coordinates of this point are going to be precisely cosine of 1, sine of 1, and 0. No. What I'm trying to, that was clear. That was obvious what I just said. What I meant to say is when this distance is 1 unit, there you go, along the curve, then we're going to be exactly at this point because of that. That is the way cosine and sine were defined, using the unit circle and using this as the input in radians. So 1 unit, because we're in the unit circle, 1 unit along the curve will take us to r of 1. I guess what I'm trying to say in this case is that in this case, t is equal to s. In this one example, yeah. If you want to be 1 unit out, all you have to do is plug in 1 into here. Now, that is not the same for in general. For the previous example, that is not true. For r, the example we were doing, that is not true. But in this case, it is the case that t is equal to s. So if you want to know where you are after 1 unit, you're going to end up with cosine of 1, sine of 1 radian, and 0. And I figured this out earlier. This is about, not exactly, about 0.54. Yep, 54, 0.84, and 0. And the reason why I want to do that is because I want to compare this with the example R. So let's draw both. P of t versus, by the way, P of t is the same thing as P of s. There's no difference. Versus R of s, which is, we're still under the same example, this big, huge formula where there's the 2 pi, the s, and all that. That is the R of example 2. So we are still working with example 2. I want to compare the two. I want to see where the point will be as s is equal to 1 in each one of those two curves. So I'm going to draw the circle first. So we're going to go about this way. So that is the projection. This is the projection. And then on top of that, or on the same picture, I'm going to draw R, which is the helix. So the helix is going to come around this way, and it is going to, after one revolution, it's going to be here. Okay, so here we have two graphs, two curves. P, which is flat on the floor, goes around and comes back to this point. This point, of course, is 1, 0, 0. Versus R goes and climbs up to here. This point is 1, 0. This is a 1, 0, 1. It's 1 unit above, directly above initial point. So the question I want to ask is, all right, if we walk along this curve for 1 full unit, where are we going to end up? 1 unit. Walk, walk, walk. Where do we end up? That's the point I showed you earlier, just a little bit ago. That's going to be cosine of 1, sine of 1, 0, which is about 54, 0.54 rather, 0.84 and 0. So this point is approximately 0.54, 0.84, and 0. Now, initially, when we started out, the x value is 1. So as we moved on the curve, this number, the x value, is decreasing. Initially, the y value is 0. So as we move on the curve, that increases. So this is reasonably close to this point. Not too close, but reasonably close. Closer to this point than to this point. All right. So the question is, what happens if we walk 1 unit along this? 1 unit on the helix. Well, it turns out that we are not going to be lined up. So we're not going to end up with this point, the corresponding point above it. By the way, all the point, man, this should have been a little stretched out a little bit. I'm going to fix it. Yeah, because we have, this should be, the bottom should be a projection of this. So there's a point here which has a corresponding point directly above it. Actually, many points above every time you go around. But the point I want to make is that if you go and climb 1 unit on the helix, we're not going to end up above this point, which was the point corresponding to 1 unit along the circle. Why not? Because as we climb up, we are using more distance. We're going up, and if this is a projection of the helix, if the circle is a projection of the helix, then we're wasting more distance by climbing up. And the question is, where do we end up? Well, to find this point, let's call it point A, and that's on the helix. So the point A is going to be R of 1, and by that we mean S equals 1, not T equals 1, because it's a little confusing. Yeah, when you write this down and you plug a number, you have to establish what the number represents. Does it represent a T value or an S value? That could be confusing. So we have to clarify which one we mean. In this case, I'm clarifying that right now. Okay, what is R of 1? When and by 1, we mean the distance is 1. So we're climbing up 1 unit. We're going to use the formula we just came up with, the big formula here. So we're going to have cosine of this. S is going to be 1. So we just end up with this fraction again. S is 1. And again, here we're going to have 1 over the root. Okay, so this is going to be cosine of 2 pi over square root of 4 pi squared plus 1, sine of 2 pi over square root 4 pi squared plus 1, comma, 1 over square root 4 pi squared plus 1. I should start using my sheets horizontally because these formulas get long. All right, so this is the exact distance, rather this exact point A, but I used the calculator because I want to compare numerically. And when we use the calculator, we end up with approximately 0.55, comma, 0.83, comma, and 0.16. So if you plug in your calculator 1 over this square root of 4 pi squared plus 1, we end up with this. So notice how they're close, certainly. I mean, the coordinates are close, 54 versus 55, 84 versus 83 hundredths. And let's analyze why. So 55 is bigger, which means we are not quite, so this point is towards us, closer to us than this point, which makes sense because we have to use up some of this distance to climb up. See, when you're going a distance of 1, we have to take into account that we're climbing up, and consequently, we're using up more distance. 83 is lower than that, which again makes sense because we don't get as far to the positive y-axis, to the right, because we're using up more distance. And we have 0.16 versus 0 because now we're above. It is very interesting to compare the 2 points and how they do not line up with one another. They do not line up. This point is before the point that lines up with this point on that curve because we have to use more. One more thing before we finish this example completely. If you unwrap this helix, start here, it climbs up to there. The slope is sort of the same, uniform slope as we move. If you unwrap the helix, you actually end up with a triangle. It's very, very interesting. So this point corresponds to the beginning, to the start, and as we climb up. And again, if you unwrap it and put it flat, this is exactly what we get. This would be 1 unit up, and the distance around is 2 pi. And by Pythagoras, we know this is going to be 4 pi squared. Square of that, add 1, which shows up in this picture. So it's interesting how we can unwrap this. Now, this is a nice function. The rate of increase is pretty constant. So that's why we obtain a nice straight line. I do not anticipate problems to be this nice in general, where if you flatten the curve, that's funny. If we flatten this, then we end up with a triangle, a straight right triangle. All right, this is a second example of arc length.